Okay, welcome back to the late morning session of the first day of FRINGE 2021 workshop. So we are continuing the ESA session. I'd like to remind the audience that you can pose questions to the presenters using Slido. So please be active. And the first presenter is Malcolm Davidson, mission scientist for the OSE-L and Sentinel next generation missions, and also the head of the campaigns unit.
All right, thank you very much. Now, I'll start off with the OSE-L. All right, can you see it?
Yes, looking good.
All right, then it is my pleasure, at least at this point in time, to present the Radar Observing System for Europe, the OSE-L mission, which is a new Copernicus SAR mission, which I believe will be of high interest to the fringe community and to the services and applications that make use of the interferometric capabilities of Sentinel at present, but in the future of L-band SAR missions. I would like to acknowledge that my co-authors here, Julia Kubanek, who is working with me on the mission, and Lorenzo Iannini, who just joined my section to help with the mission requirements, as well as the OSE-L project, Robert Fresnel, Nico Gebert, Steve Osborne, and Dirk Geithner, who are working very hard on making this mission possible. I give you a little bit of background. First of all, the ESA developed Earth observation missions. As you can imagine, the missions have been expanding considerably over the past 10 years, a lot actually. When I joined in 2001, we had one SAR mission, well, two actually, with the ERS and MVSat. And now you can see how this suite, this family of SAR missions has expanded with Sentinel-1A, 1B, Sentinel-1C and 1D in the future, and the Biomass mission, which we'll be hearing more about later on. Okay. In addition to those missions, we have the Harmony mission, which is an Earth Explorer, and the OSE-L and Sentinel-1NG, which have respectively one presentation each in this session. Right now, I'll be talking about the OSE-L. I'll give you an impression of the mission, its capabilities, its origin and objectives, and then maybe finish with a nice slide, giving you one of the first artist's impression of what the satellite will look like in the future. First of all, coming back to some of the sort of raison d'etre of these new missions, as part of the Copernicus program, there has been an effort to look at what we now call expansion missions, which were high priority candidate missions, so you might have come across HPCM before. Now they are called expansion missions, and they address mainly gaps in data, gaps in information for services and applications. So operational services and applications, much in the way that Sentinel-1 does. And they're a diverse lot. You can see that they have, they go range all the way from atmospheric missions looking at CO2 to optical missions looking at, for instance, land surface temperature. But the OSE-L, so the Radar Observing System for Europe at L-band, is one of these 6 missions, just to situate them programmatically, and has been extensively studied since about 2017, if I remember correctly. What are the OSE-L mission objectives? Just to give you a quick overview. Number one, as I mentioned, is this idea of filling gaps. So information that does not yet exist from, shall we say, Sentinel-1 or other types of missions. And that is made possible by adopting a longer wavelength in space and adopting also the Copernicus characteristics of our mission. So frequent observation, coverage, consistent modes, and so on. Having gone through this process, we've identified together with the user and applications community several important objectives. The ground motion information under vegetation is one, using the longer frequency. And you have a nice example of this sort of filling of gaps here on the right-hand side with L-band image taken, I believe, in that case, over 40 days time interval compared to a C-band image of the same area. Here, color, this community will know it quite well, but the color indicates information on the surface displacement. And and you can see that there's a lot more color, just to put it very simply, in the L-band image than in the C-band. There are many other areas where L-band SAR in a Copernicus-style configuration can help. Enhance high-resolution sea ice information, soil moisture information over land use change, the sensitivity to biomass and to crops is higher. Soil moisture, of course, underneath vegetation, and a few others. And then there's this idea of enhanced continuity. There's also a driving motto or a driving paradigm in the Copernicus SAR missions. And here we have enhanced revisit simply by the fact that C and L-band will be flying around the same time. And that the combination of L and C-band, and that's a recurring theme in some of these presentations, is expected to yield new insights and new information than a frequency by itself. Here's an example that we went through for sea ice. You have on the left-hand side the user requirements were the responsibility of the EC, and we had to take those, and we did, and basically go through all of these requirements and see what it means for the ROSE-L mission. And you have an idea of what the outcome here is here on the right. All the green little tiles there, the chiclet-like products are products that were identified in the Polar Expert Group information products, and for which ROSE-L can make a significant contribution, like grounding line, for instance, and some of the ice sheet surface motions, as well as sea ice. Here's an example of sea ice, just to leave interferometry for just a bit, but give you an idea of some of the potential. Here you have areas where you're comparing for the same area L and C-band. And you can see that for brash ice and sea ice ridges, you have much more information, much more easier to map at L-band than it is at C-band. This is well known since a long while, but it's particularly these areas that are important to know for instance, shipping. You do not want to go through big sea ice ridges, even with fairly large ice breakers. Okay, if we come to system and instrument requirements, we're talking about 2 satellites, 85 megahertz bandwidth, so we're using the as much as we can. Here you have a nice image of the spacecraft, by the way, at least the artist version of it. Spatial resolution is higher than the Sentinel interferometric wide swath mode, 5 by 10 meters, considerable jump in resolution. Revisit time fairly similar to Sentinel, mostly because the swath is the same. One thing I would really like to draw your attention to is that the ROSE-L system, or the ROSE-L missions, will operate at the same orbit and with the same acquisition geometry as Sentinel, so that you effectively, have a 2-frequency system of systems in space once they're all launched. Also draw your attention to the low noise equivalent sigma 0, which should help to the signal to noise. It's right looking, so we've prioritized the Arctic, mostly due to programmatic reasons and to the EC requirements. And here we have some more of the elements that I would like to draw out. The average orbit duty cycle should impress you, I hope. Nothing worse than having a silent SAR satellite pass over top, as you would like an image. And in this case, the average orbit duty cycle that the industry is working on now is 38 minutes, which is a big jump from the 25 of Sentinel, and 56 minutes maximum. Systematic, we keep the tried and tested elements of Copernicus, systematic observations, and a reduced number of modes to avoid conflicts. Okay, one or two more slides, just to give you an idea, maybe putting together in a single diagram the next step in spaceborne mapping capability. So what is the step forward? Well, technology has evolved since the original developments of Sentinel-1, and now it's possible to offer wide swath, high resolution, low noise equivalent sigma 0, good ambiguity performance, dual pole, quad pole modes for the L band, put all of this in a relatively small launcher together with high duty cycle. And that is how we intend to satisfy the needs of the Copernicus users. It's challenging, but it's feasible. Conclusions and future perspectives. So just to draw your attention to a new Copernicus SAR mission, the OSE-L mission at L-band, addressing new information, the enhanced capabilities of higher resolution, low equivalent, noise equivalent sigma 0 and wide swath. Sentinel-1, OSE-L and Sentinel-1 NG are addressed as a system, so we treat them not in isolation. For instance, the OSE-L has the same orbit swath and acquisition geometry as Sentinel-1 again. And I expect, and I think a number of other scientists and application experts we consulted expect also a lot between in the synergies between C and L band. However, it also means, and that's perhaps the exciting part for the wider community, that there's quite some work required to prepare for OSE-L. And I'm thinking of things like your applications, but also basics of correcting the ionosphere correction, interferometric error budgets, and C and L band synergies. And with that, I would like to close my presentation.
Thank you, Malcolm. I think there was we are not fully following the program, so two presentations were swapped. That's okay. So next one would be, according to the program, Björn Rommen to present the mission and system status of the ESA's biomass mission. Yep, it's up.
Yes, good morning, everyone. Welcome to the session. Okay, so I will briefly, you can hear me well, I guess, yes? So I will start with providing, let's say, an overview of mission system status of ESA's biomass mission, which is Earth Explorer 7. Next slide. Okay, we'll give an overview of, let's say, the mission objectives, the key mission requirements, the biomass orbit swath considerations, which is quite interesting because we're operating this LEO SAR in quite a different way than we used, let's say, from other missions you've been hearing about, so we'll be hearing about today. The overall mission operations concept, the system architecture, some mission performance estimates, and the current status and outlook provided, given, let's say, that the mission is currently, let's say, in its critical design review. The biomass satellite, industrial prime contractors, Airbus Defence Space in the UK. Also, the radar instrument itself is also built by, let's say, Friedrichshafen and the avionics Airbus and Toulouse. Of course, they are supported by an enormous large team, let's say, of subcontractors and other subsystem deliverables, let's say. The key mission objectives are, and there's also some mentioned by Maurice Bourgeot this morning, to determine the distribution of the above-ground biomass in the world's forests. Also to measure the annual changes in the stock over the period of the mission, which is supposed to last, let's say, for 5 years during the operational part of the mission, so excluding the commissioning phase. We need estimates of forest biomass, height, and disturbances to get access to this. To these, let's say, mission objectives to actually quantify those. It's important to mention that the mission must resolve the tropical biomass question and so be capable of monitoring these high biomass stands. Nearly all the land use change flux is actually located in the tropics. The biomass measurements are needed at the scale of roughly, let's say, a hectare scale. The appropriate resolution is about 4 hectare, which we believe is a scale at which the ground data are reliable and available, but also, let's say, is the key scale of landscape heterogeneity. The accuracy must be around 20% for biomass, comparable to the field observations that we have. Deforestation detection, also at finer scales than a biomass product. So we're looking at actually 0.25 per hectare. Will provide further information for understanding of the biomass change. And the mission was run then for multiple years to have multiple repeated measurements of multiple years to identify these dynamical processes. So in short, let's say the overall mission summary would say to take stock of the biomass in the world's forest and to monitor its evolution during the lifetime of the mission. The primary objectives, as I said before, let's say determination of forest biomass, forest height, vegetation disturbances, and regrowth. But there's always, let's say, also secondary objectives. One is to image the subsurface geology in deserts, getting access, for example, to paleo rivers. And then mapping mapping topography in the dense vegetation because of the low frequency. We're operating at P-band, 435 megahertz center frequency. We actually are getting sensitive, let's say, to the actual forest ground, let's say. So and as such, I say, we'll be able to get access as well to digital terrain model underneath, let's say, the forest canopy. And the third one, let's say, is the measurement of glaciers and ice sheet velocities in the Antarctic, especially. The overall coverage, let's say, of this system, I think it's important to show this feature system. We got systematic acquisition for forested land, which are the red areas on both ascending and descending orbits. Biomass will be, let's say, a global, acquiring data globally. Although, as you see here, let's say we have an area, let's say, where we're not supposed, let's say, to transmit an acquisition mask. It's restricted by the US Space Object Tracking Radar Network, which is operating at the same frequencies. And in the ITR, the time, let's say, the allocation was made to P-band for spaceborne sensors. It was decided that we should not transmit unless coordinations have resolved, let's say, and we're able, let's say, to access these zones. So for now, at least, this is the bottom line. That's that we are not acquiring data over North America and a large part of Europe. This may change, however, let's say, from future, let's say, consultations with the US Air Force. Global coverage, let's say, is less than 9 months for the interferometric phase and less than 17 months for the tomographic phase. Important to say that this will be the first mission that will have an operational tomographic phase. Best effort acquisitions are done from non-forested areas, so the yellow and the ocean sea ice region of interest. So the information is forest biomass, forest height, and disturbances. The above ground biomass is at 200 meter resolution. The accuracy is about 20%, 10 tons per hectare for biomass less than 50 tons per hectare. The upper canopy height is at 200 meter resolution as well, with an accuracy of 20 to 30%. And disturbances, as mentioned before, let's say, is with a 50 meter resolution and with a 90% classification accuracy. So we get one map every 8 to 9 months of all forested areas, excluding, of course, the Space Object Tracking Radar Network regions. And how to access, let's say, how to get, let's say, these products. Actually, we are using biomass in 3 different ways, let's say. So we have using as a for SAR polarimetry. So you can use actually your favorite decomposition that you want to use. Polarimetric SAR interferometry, where we'll be able, let's say, to get access, let's say, to the height of the forest. And then as well as SAR tomography, where we're able to make, let's say, a vertical profile through the forest canopy. And all these tools will be used, let's say, in conjunction, let's say, in synergy to get access, let's say, to the forest biomass. So operating at P-band has we know that P-band backscatter has high sensitivity to biomass compared to other wavelengths. We're about, let's say, factor 12 lower in frequency compared to Sentinel and factor 3, let's say, when we compare it to L-band systems such as OSE-L. So there are some advantages, but on the other hand, we have as well some disadvantages, let's say. So we have a very high temporal coherence over repeat passes, which is very good. But on the other hand, let's say, we are very susceptible to ionospheric distortions, which we have to take into account, but also, let's say, due to the large wavelength and large antenna diameter. For example, we have currently no test facilities which would allow end-to-end performance testing on the ground. So that means we have to rely on dedicated antenna pattern characterization in orbit. To achieve the level 2 performances, the system has to comply to high accuracy polarimetric and radiometric requirements. It's a full pole system. We have two actual mission phases employing multipass interferometry, where of course we have controlled inter-orbit distances between successive revisits to the same site, and then we'll get to the actual orbit swath considerations later. So with a specific tomographic phase, which we're going to start the mission with, of observations with 6 3-day baselines. So we make 7 acquisitions. And we have an interferometric phase, which will follow, let's say, the tomographic phase, and which will be repeated during the later mission lifetime, where we have observations with 2 3-day baselines, so 3 acquisitions. So Biomass operating in a 666 kilometer down-disk orbit. We have a 3-day repeat, 44 orbits, which you can see basically here on the right. We employ a very small east-west drift to implement baselines. So you can see this this is swath 1. So every time, let's say, we have a strip map, we're operating Biomass actually in a strip map mode at 6 megahertz bandwidth. This is the allocation that we have, 432 to 438 megahertz. And we have a satellite. We have to employ satellite role for swath access. So with all the fancy ScanSAR systems you're working with, this is maybe a couple of steps back. On the other hand, let's say there are some really nice challenges, let's say, to the mission itself. But we have to employ a satellite role, which means that, of course, we cannot do this during a single overpass, which means that after let's say, a certain amount of time. So, for example, we would be in interferometric mode, in interferometric coverage mode, where we have to make 3 revisits. We would go over 9 days. We would make the 3 visits, let's say, in swath 1. Then we would roll the satellite to swath 2, and we do the same thing. And then we do the same thing for swath 3. And after 27 days, we basically have this covered. Which means that now we have to do something else. We have to actually then jump, let's say, after what we call then a major cycle, after this 27 days. We have to then move to do a satellite repositioning maneuver, where we actually are going to cross over, say, raise the altitude to have a faster east-west drift, move this roughly, let's say, 150 kilometer of swath, let's say, total swath, land again, let's say, and repeat the procedure again to get the next major cycle. And as such, slowly, let's say, we're filling in, let's say, the actual global coverage. And then after a while, let's say, we then do again that satellite reposition maneuver, and basically we start again with collecting data. The overall system architecture will consist of Biomass for like any other satellite system, let's say, consisting of a space segment, where we have a platform as the Biomass SAR payload and the large deployable reflector, as well as a ground segment consisting of a flight operations segment and the payload data ground segment, and as well as a Biomass calibration transponder. And we'll launch with Vega from FRINGE2021. The overall spacecraft design, we have a large deployable reflector, an offset feeder reflector antenna system with a 12-meter aperture deployable reflector. Satellite avionics will be based on the Airbus AS250 platform. And the OSE-L architecture provides serial Doppler steering and ball steering to ensure compatibility with the deployable reflector and to meet the overall SAR mission performance needs. So here you can see, let's say, where actually everything is in deployed configuration or installed configuration. This is actually the Biomass structural model with the reflector boom, let's say, installed launch configuration. Let's say a lot of tests are ongoing, let's say, with the engineering models and engineering qualification models. This is a structural model of the spacecraft. Then the overall Biomass SAR payload, I will go into this to show a bit, let's say, the inside of the instrument itself. So the overall payload consists of the instrument itself and the large deployable reflector. We have the feed array that is transducing the RF signals to the actual instrument electronic system, which consists of the power amplifier subsystem and the receive amplifier subsystem, which is called PAS and the RAS, calibration distribution network, and a digital control unit, which is performing the instrument control, shunt generation, and receive signals sampling. So very quickly to go through, let's say, the actual generation of the signal. As you can see, let's say here showed for one polarization. We have the feed array consists of 4 patches, which are fed, let's say, per 2 patches, and each of these 2 patches we call it the doublet. So they're all fed, let's say, per 2, let's say. So per 2 patches. And then if I click yes, then basically this is the transmit chain, and on receive comes through, let's say, the patches. Then actually there's a circulator, let's say, and actually summation, and then come to the RX sampling. And of course, when we go, let's say, since this is a full pulse system, we of course we're transmitting in NH, we're receiving in VNH, and then the same we do for the next PRI, we're jumping, let's say, to the V polarization. What's important, the takeaway message here is that we have separate power amplifiers per polarization, and we have dual polarization FA patches, which are, as I said, operated per doublet. So we don't need any fast, let's say, high power RF switches, which you need for full pole polarimetry. So here you see the actual overall, let's say, all the engineering qualification models that are currently, let's say, being tested. The feed array, the actual L3 Harris, let's say, reflector, which is now actually been converted now to actually flight model readiness, the DCU, and the calibration data network. The mission ground segment, let's say, the ground segment is composed of the major elements, let's say, flight operations segment, doing all the TMTC, communication with the spacecraft, mission planning, satellite control, status monitoring, orbit and energy determination, and onboard software maintenance, also the PDGS, the payload data ground segment, which is implementing all science data functions. Then we have as well, let's say, the biomass calibration transponder, which I show quickly here. This is, as you can see, let's say, operating at P-band has quite some challenge as well, because of the large wavelength. All things scale up, let's say, quite considerably. As you can see, the actual array here that you see here is on nearly 5-meter diameter. And this is almost, let's say, you can almost is a full building, as you can appreciate here by the actual access doors here underneath. Then a few notes on the actual mission performance. So we have a sensitivity, let's say, better than -27 dB, so noise equivalent signal not. Total ambiguity ratio should be less than -18 dB. The SLC resolution is about 60 meter by 8 meter, and dynamic range of 35 dB. And the radiometric stability of half dB. Cross target.
Björn, you have 2 minutes.
Yeah, I'm nearly done, Marcus. I've got one more slide. So the overall status and outlook, let's say the satellite platform avionics testing has been completed. The satellite structural model has been fully assembled, and testing has also been completed. Instrument electronics and engineering qualification models have been integrated, functional testing completed, and currently actually performance testing are still ongoing. Ground segment development is well underway. Both FOSS and PDGS design activities are ongoing. The biomass calibration transponder development and prototyping activities are progressing, reaching as well soon, let's say, before in summer we start as well the critical design review of the biomass calibration transponder. The system CDR is, as I mentioned, currently ongoing, and we're actually foreseeing a launch, let's say, for Q3 2023. And my last slide, I'd like to acknowledge, let's say, all the people involved, let's say, in the biomass project. So this concludes my presentation, Marcus. Back to you.
Very good, Björn. Let me just take over briefly here as chairman. Thank you, Björn, also for sticking to time. We are right on time. We'd like to proceed then with the next presentation. Now, some of you might have noticed a slight change of order. We've actually started with the lower frequencies and the longer wavelengths. And we now move to the higher frequencies and the well-known C-band emissions. And we have a very nice presentation here scheduled from Guillaume Hajdouche, who also worked on Sentinel 1 and OSE-L next generation, by the way, who will present the Sentinel 1 product performance status. So with that, I would like to hand over to Guillaume. One more thing, though, before I do. Please consider posing your questions on the Slido link that you all have. There's about 2 or 3 questions so far. And I, together with Marcus, would like to see a few more so that we can discuss them at the end of the session. So with that, I hand over to Guillaume. Please take it away.
Okay, hello. So can you see my presentation?
Confirmed. Everything looks good and I can hear you fine. So please go ahead.
Okay, so perfect. So I will present the status of product performances for Sentinel-1 mission. So these are results from the Sentinel-1 Mission Performance Centers with a presentation made here on behalf of, on request of Gesa. So this is a joint work by many people who are seated in this first slide. Okay, so here are the outline of the presentation. So first, the status of the antenna, pointing, then the radiometric calibration, geometric calibration, instrument and processor updates, and then the conclusion of the status of the product performances and planned evolutions. So first about the Sentinel-1 antenna status for Sentinel-1A. So you can see here diagrams representing the errors in the gain and phase for the antenna panel in the various polarimetric configurations. So there are some marks in the diagram in the left corresponding to transmit and receive modules that were in failure or that are in failure. And in the right, you can see the complete history of the antenna failures. So you can see that even if some of the antenna modules are in failure, nothing new occurred in the last months and especially in the last year. So this means that the antenna status is for now pretty stable for Sentinel-1A. For what concerns Sentinel-1B, so you can see as well that some TRM, transmit and receive modules, are in failure as well, but far less in error compared to Sentinel-1A, mostly due to the fact that Sentinel-1B is more recent. And you can see in this history of failure that no recent change occurred in the last months and even years. Here is some results about the Sentinel-1 Doppler Centroid. So this is an estimation of the Doppler Centroid as recorded by the instrument here. With this diagram presented the various star tracker configuration for Sentinel-1A. So you can see that various star tracker configuration are used with time, depending on the restart of the star tracker or even instruments. And at some restart of or change of configuration, we can observe some jumps in the Doppler centroid, which corresponds to different intercalibration of those various star tracker usage. The same diagram for Sentinel-1B shows a smoother variation, most probably because the star tracker are more accurately calibrated for Sentinel-1B than for Sentinel-1A, but still we can see some seasonal variation with smooth variation. So it is expected that a recalibration of Sentinel-1A star tracker will induce smaller jump in Sentinel-1A compared to Sentinel-1B. Okay. Now about the Sentinel-1 radiometric calibration. So this is performed through measurements on transponders. So here are results from a transponder operated by DLR. So those are a long time series of measurements in IW, VV, VH, actually both on corner reflector and transponder on the diagram on the top, which shows quite stable radiometric calibration. And with the table on the bottom show you the mean value and standard deviation of the radiometric accuracy, which is actually within the Sentinel-1 expected product performances, knowing that we continue to work on improving this as far as possible. Oh, something strange is occurring. Okay, sorry. About elevation antenna pattern updates. So during 2020, the elevation antenna patterns of IW and EW mode were updated several times to improve the radiometric quality of the product. The rationale of this elevation antenna pattern update is to assess the flatness of gamma profile over the rainforest and to compensate the elevation antenna pattern accordingly so as to obtain flat antenna pattern in the for gamma profile acquired over the rainforest. So here are some updates performed in 2020. So in December 2020 for EW dual pole H configuration for S1A, in May 2020 for S1B IW dual pole V, and one for S1B EW dual pole H and dual pole V in December 2020, knowing that a last update was performed in January 2021 for IW dual pole H configuration. So the diagram in the right shows you the work that was performed here with variation in EW mode with update of the elevation antenna pattern for S1B in yellow. So on the top, this is before the optimization of the elevation antenna pattern, which shows slight variation across off-bore sight angle. And thanks to this update, this is now much flatter, which allow improvements on overall radiometric calibration across the swath for this mode. So each time such update of elevation antenna pattern is done, we update both the characterization of the pattern and the overall calibration of the product so as to ensure radiometric stability on long term. So now some elements on radio frequency interference contamination. So a small percentage of S1A and B imagery is affected by radio frequency interferences. So this can be due to RFI sources from the ground, being for instance weather radar or military radars, or in some configurations from other remote sensing satellite in C-band like RadarSat-2, GeoFence-3, RCM, or sometimes from unidentified sources. So some maps of RFI contamination probability based on analysis of top SAR rank equals are available on the website, which is cited here. You have some example of such configuration and of such contamination on the right, and we are introducing an RFI mitigation feature in the Sentinel IPS that I will demonstrate later in the presentation. So about the status of evolution of product configuration for the last year. So there were two major updates of configuration related to deployment of new processor version, one in January 2020 and one in June 2020 as well. So the first one was about to update the geolocation grid annotation. So this is for coarse annotation of geolocation of the product based on this geolocation grid. And other update is to support the new type of auxiliary orbit file called restituted orbit files. Preliminary orbit file, which have similar performance as the restituted orbit file, with the difference of pre-orb being available shortly before the acquisition, while resorb are available a bit after the acquisition. And the second update in June 2020 was performed to fix some specific production issue on the PDGs without on the ground segment without change of the product performances. So for the main updates on the productions, for what concerns the product performances and quality in 2021, so this is first this RFI mitigation through a combined time and frequency domain approach, and the annotation of top SAR burst identifier. So here are some examples of the expected performances. So on the left, you have some example of a product contaminated by RFI on the top, and on the bottom, a product after mitigation of this RFI. So you can see that most of the contamination was removed. One important point is that the processor will be able to remove as far as possible those RFI, but as well to annotate the presence of those contamination and whether it was mitigated or not. And the second element is the annotation of a burst ID, absolute burst ID for the TOPS modes, which will allow for the user to identify more easily each burst, depending on their position within the acquisition, with a rough correspondence to geographical area limited by the burst cycle. So this could be of interest for filtering of ID of bursts for INSAR applications. So some conclusion and way forward. Sentinel-1A and B instrument stability is very good. Some DC jumps are affecting S1A after some star tracker changings, and they are monitored. And this could be updated or refined by new star tracker alignment campaign. Sentinel-1 radiometric calibration is well within the requirements. Correction of elevation antenna patterns for IW and EW beams are performed regularly to improve this. This was not demonstrated in this presentation, but some gain adjustments were performed on the wave mode as well. Sentinel-1 calibration is well within the requirements. Just to mention that Sentinel-1 products can include radio frequency interference contamination due to ground and space emitters. So this is planned to mitigate them and to annotate the RFI in 2021. And finally, the burst ID annotation will be introduced in 2021 as well. If you want to have more details on the performances of the product, so you can refer to the last annual performance report for 2020 first, and to the Sentinel-1 product specification. So both are available on Sentinel Online, mentioning that a new version of the Sentinel-1 product specification for the future IPS version was published in advance for the user to see how to accommodate and use properly the RFI annotation and burst ID annotation in the product. So this concludes my presentation.
Right. Thank you very much, Guillaume, and also for sticking to time. I hand over to Marcus now to introduce the next presentation.
The next presentation is by the Sentinel-1 Next Generation Mission Scientist, Malcolm Davidson. Malcolm, you have the floor.
Right. Thank you very much. Let me just share my PowerPoint presentation. And, right. So it's my pleasure to switch frequencies and go from L-band to C-band to explain the current status of a different mission, which is the follow-on mission to the current generation of Sentinel-1. Well, one of the challenges that we've had is how do we name Generation 1 and Generation 2? Keeping in mind that NG in this case is the next generation. So if you see in some of the ESA documents now the acronym S1FG showing up, that's the first generation, and not to be confused with the satellites that I'm about to present. So I would like to give you an overview at this special point in time. And I would like to start off by acknowledging also my co-authors, Julia Kubanek, who works with me and will be working in the future on some of the mission requirement consolidation studies. Ramon Torres, the project manager, and the project team building on David Bibby and Dirk Goitner. So in this presentation, I'm going to start off with the same slide as I did for the OSE-L, just to give you a feeling for where we're at. Again, given the sheer number of missions, I think it's important and a challenge not only for the outside community, but sometimes inside ESA too, to situate where all the missions fit. And go back to Sentinel-1A and B that you know quite well as part of this community. Sentinel-1, C, and D that are coming in the near future that are also, I think, eagerly anticipated by the Fringe community. Biomass, where we had a nice presentation from Bjorn just a moment ago. Harmony, as just to give a precursor or a preview to the presentation after me, and ROSE-L and Sentinel NG. And those are, roughly speaking, also in time, the way the things will go. So it is quite a future for the SAR community and for the FRINGE community in general. Maybe some general characteristics of the future Copernicus SAR missions before I delve into some of the details of Sentinel NG. These are respected both by ROSE-L and by Sentinel NG. The systematic acquisitions combined with large swath and high resolution and high duty cycle. Those are all driving elements of our mission that we continue to maintain and even enhance in the future missions as technology and industrial know-how allows us to. Enhancing consistent time series and a commitment to long-term data continuity. So that's exactly one of the reasons that we are starting with Sentinel NG, now just about to start the phase A, with an eye on ensuring that this long-term continuity is managed and implemented correctly, so that all the developments around Sentinel-1 and in the future ROSE-L can be continued. Interferometry, low data latency and enhanced data streams for AIS. Interferometry is built from the very beginning in our missions, and Sentinel-1, NG, and ROSE-L are no exceptions in that manner. The high availability and redundancy for the procurement of multiple satellites, at least 2 satellites. The new parts, I've already talked about it in ROSE-L a bit, the multi-frequency, which is the C+L, and perhaps less evident, but showing up a little more in the presentation after me, is this idea of having satellites that are companion-friendly. In other words, that they have very stringent requirements, for instance, on their onboard timing that can support, in some cases, an option for a sync link that could support future additions to a sort of reference infrastructure. Now, going through the Sentinel NG requirements, we're in this process since roughly 2.5 years. It follows a well-defined process, which is starting from European needs and requirement sources. So it is not me sitting in a room that is writing down simply what the objectives of the mission are. We take as inputs and as user requirements the output of here, these EC working documents. There was a big EC user requirement study that the mission responds to. The EC organizes a number of user workshops and task forces. And all of this is also connected to the European needs in general. A good example is choosing coverage of the Arctic with respect to the middle of Antarctic in particular, because there is an EC Arctic policy that we need to respond to. And we go through the various types of requirements, the observation gaps, enhanced continuity and continuity, the mission objectives. Then we come more to the mission requirements, trying to summarize these, also including the international context, what kind of information the product has to generate, and finally the mission specification and the system requirements. And the process at high level looks okay. You can see many different arrows. And believe me, I've thought about each one of those arrows, so they do mean something, and they're not just put there to impress you. Then we go, just to give you in a nutshell, a sort of overview of the Sentinel NG high-level mission requirements and status. Number one objective, and let me be very strong on this, the number one objective is to guarantee continuity of data availability with Sentinel-1. In other words, all of the investments in services, applications that have been made at European level and at downstream level, we try to ensure that these investments will be even enhanced in the future and not affected in a negative way by the switch from Sentinel-1 to Sentinel-1 NG. And believe me, that is also a tricky subject, one that we are studying intensively with the mission advisory group. And I'll give you an example later on. Okay, simply continuity of C-band data beyond the next decade, 2030. A basic requirement then is that you do not go back in data quality, but it should at least be equal or better than Sentinel-1. So it's a sort of logical conclusion that comes out of it. In many cases, in fact, in most cases, it's better also allowing for evolution in technology. There's the element of enhanced continuity. Okay, Sentinel-1 is there and doing an excellent job, as we've seen in many different presentations and a number of presentations in this workshop, but we can always improve in terms of higher spatial and temporal resolutions. And it's good to know that there's always been there has been a cross-cutting user requirement for higher resolution. That's a very strong one coming from the EC and from the services. We're looking at quad pole, a wider swath as a consequence of the revisit. Lower noise equivalent sigma 0 that reduces the biases and improves strategies like the noise floor subtraction, gives you more signal in areas that are fairly dark. Investigating some new approaches for ship detection and ocean currents. It's a companion-friendly mission, as I mentioned at the beginning, strict onboard timing requirements to support synchronization. And we're also keenly aware of the role that Sentinel-1 NG can and will play in the overall context of commercial space and developing commercial space applications. So there's this idea, and that's part of the phase A for industry, to look at some architectural elements and how Sentinel-1 NG will operate with, shall we say, future developments, future services, such as the ISIs of this world and that type of thing. In terms of mission status, and then you will see why this presentation is a bit of a challenge, because we're actually between phase 0, which was a pre-feasibility exercise study, which was finished around the end of 2019. I think some of the elements were closed beginning to 20. And the phase AB1, which is about to start. So in terms of shall we say, we're between phases, so I can present some of the performance aspects that were studied in phase 0. But keep in mind that phase A looks at different implementation options with European industry. And so that various elements will be traded off in terms of implementation. Some of these requirements will be assessed in a very critical way. And I want you to keep that in mind. And I just outline it as a sort of challenge of presenting Sentinel-1 NG at this particular point in time. I expect by Fringe next year or in the coming years that we will have a lot more information on the actual system. Okay, this is just an illustration of the various phases. So when we talk about continuity, we have Sentinel-1, which is ongoing, of course, and then there will be an overlap with Sentinel-1 NG. There's also an overlap with OSE-L a little earlier. The services are continuous. We have to ensure that as we go through these different phases, that's just focusing on Sentinel-1, Sentinel-1 by itself, so the classical constellation, Sentinel-1 plus Sentinel-1 NG, and then Sentinel-1 NG by itself. So those are elements that we have to keep in mind. And a good example of the challenges is provided here. We aim to provide the guarantee of continuity of services, for instance, for the new European ground motion service. And this requires a careful trade-off if you consider these types of maps. You have the challenge that you would like the system to evolve with time and have new capabilities. But, well, just to give you some insight, do you, for instance, keep exactly the same geometry, in which case you restrict the system a lot to keep the same persistent scatterers? Or do you put some requirements on the overlap time between Sentinel-1 and NG, Sentinel-1 NG to ensure continuity? Those will be studied in the future. I just illustrated as one of the challenges of the and part of the process. Now coming to the industrial part. So we had the phase 0, which were 2 contracts run from 2019 to 2020. Identification of generic user needs and some mission assumptions to investigate what the space system can do. So these are building blocks that, a bit like Lego blocks that go into the phase AB1, which is the process right now. You have there, the ITT was issued the 15th of December 2020 for a 2-year contract. And now we're looking at the feasibility. And then in the future, we will look into the actual implementation once the phase AB1 is finished. The whole thing is guided by a mission requirements document. and also by a mission advisory group that will meet for the first time, I believe, next week or the week after. So we are moving forward on these different elements. I'm hoping there's a lot of young people in the audience, because also the launch, of course, and the implementation of this mission will take some time. And we're looking at the potential launch beginning of the next decade. Now, just to give you at least a feeling for some of the things that came out of the phase zero, this is the performance that was identified in the phase zero. So you can recognize some basic things like improved global coverage, less than every 4 days. Now we're aiming for every 3 days, to be honest. I'm sure this number here in 53 minutes will take your breath away. That means it's it's on over half the orbit, which is a lot for a SAR mission. In fact, if you add the wave mode, it's probably on much longer. But this combination of wide swath and high resolution, 5 by 5 meters, that's a huge improvement in terms of resolution. And yet we still have the same swath, if not better swaths than we've had so far, so improved revisit. Some sort of ideas to improve ship detection, for instance, using a long track interferometry are also around. And improving latency and so on. That's just to give you a feeling. These numbers are going to be revisited in phase A, but at least you can start getting some feeling for where the system is going with that. There's a nice illustration of the synergy where you, if you put, for instance, the two OSE-L missions and satellites and the Sentinel one together, what kind of revisits do you get? And it just illustrates the synergies. For instance, if you go to an optimized revisit constellation, you get a huge improvement in terms of the main revisit. Okay, at the end of my presentation, what I can do for between phase 0 and phase A. But first of all, just to remind you, the Sentinel-1 next generation at C-band is there to ensure continuity of services and applications relying on Sentinel-1. Enhance the existing services and applications. So the idea is not to stand still, but to enhance and respond to the evolution of services and applications. Enable new applications as those become available through the improved performance, and perhaps some observation gaps can be addressed. Phase A is just about to start, so it's an exciting time. And the phase A will look at the trade-off of different implementation options, and also look a little at the architecture. So how can we use Sentinel-1 NG together with the expanding commercial and new space sector? I can assure you Sentinel-1 NG will bring new and enhanced capabilities. We've already shown some examples of the resolutions that are feasible. The low noise equivalent of sigma 0 will help for applications in areas which are fairly dark with respect to radar. The wide swath and frequent revisit capability. And I would like to emphasize that we are treating this as a system of systems, so that for instance, the overlap between Sentinel-1 and Sentinel-1 NG has to be considered carefully. The joint use of Sentinel-1 and OSE-L have to be considered together very carefully. And the launch dates are, I'm not a big fan of giving you exactly the launch dates, in part because they're still evolving, but we're talking about the 2030 plus time frame. And with that, I would like to conclude my presentation.
Thank you, Malcolm.
All right, and then I take the opportunity to go from my presentation to another presentation that makes excellent use of the Sentinel-1 mission. And I would like to introduce a good colleague, Paco Lopez-Decker, who will give you all of the details about the Harmony mission, the mission concept, science objectives, and performance. He is the best person placed to give you that overview. So with that, it's all yours, Paco.
Thanks, Malcolm. Are you seeing the right screen or are you seeing the wrong screen?
You have the wrong screen.
The wrong, it's always the wrong.
That's Murphy's Law, that the wrong screen.
Now you see the right one? Okay, very good.
Yes, now
Thanks. Very good. So talking about systems of systems, we are going to add more systems to the systems of systems with harmony, and hopefully in harmony. And this would be the ESA official title slide, but let me start with the title slide of this talk. And Harmony does lots of things. I will talk a bit about that. But in this talk, I want to focus mostly on the things that are more relevant to the FRINGE community, which is retrieving 3D surface velocities on solid earth, and also looking at glaciers and volume changes over glaciers and overland. But this will come in a few minutes. Maybe I should acknowledge, typically I don't do it, but I'm really talking on behalf of the Mission Advisory Group, and a lot of the material that I'm presenting was prepared by people in the Mission Advisory Group, and the people that you can see are the ones who were involved in this part, in these topics, including Helmut, who is not in the MAC, but who was a very vital part of the mission. Now, I want to start with an overview, a general overview of the mission, and then we'll switch to the FRINGE more relevant topics. But in general, what we want to do with Harmony is to look at small-scale motions and gradients of the motions happening on the surface or at the surface. And the Earth is big, and most of the Earth's surface is not solid Earth, it's oceans, so we want to look at the oceans. And there we're targeting small-scale motions and small-scale gradients of surface currents, but also the surface winds, which we want to study, to acquire, in order to improve our understanding of exchanges between the ocean and the atmosphere, which of course are very important for climate. We also want to better understand ocean atmosphere extremes. That's an expensive term for tropical cyclones and extratropical cyclones or big storms. Now, going a bit more into FRINGE, over glaciers, so we want to look at glaciers worldwide, and we want to look both at gradual, so multi-year changes of ice volumes and associated mass balance changes, but also at the dynamic processes happening at seasonal scales. And we have a bit of sea ice, but I will not cover that. And then when we go to the solid Earth, our main goal is to retrieve tectonic strain, and to do that we want to get 3D deformation vectors everywhere where tectonic strain plays a role. And then as a secondary goal, but also as a very attractive goal, we want to improve our understanding of the volcanic cycle by looking at the changes of volume, either prior or after a volcanic eruption. Now, let's continue with a cartoon of the mission. This is, again, a slide that I used to illustrate the mission in general. But what we want to do is to add 2 companion satellites to Sentinel-1. So we will have 2 satellites flying in formation with Sentinel-1 at a few hundred kilometer distance, so 300 to 400 kilometer distance with respect to Sentinel-1. Sentinel-1 will do its thing, transmit, receive, make nice images, and then we will acquire, so we will receive bistatically the radar signals scattered in other directions with the Harmony satellites. From a system point of view, we hope that we are not impacting Sentinel-1. We just benefit from it being there. But from a science point of view, we consider Sentinel-1 as an integral part of the mission, because we are not happy with the 2 lines of sights that we get from this geometry. We get the 3. We get Sentinel-1 plus the 2 with the 2 Harmonies. Now, in this community, in FRINGE, you all understand that we can retrieve motion with radars. And then you also immediately understand that if I have 3 different line of sights, I can get 3 components of the motion. So that's trivial. We can do it over land using repeat pass interferometry, but also over oceans by looking at the Doppler of reduced surface motion by ocean currents. Something which is not FRINGE specific, but which is nice, is that you can do scatterometry. So when you look at the ocean surface from different directions, because the backscatter is wind strength and wind direction dependent, having these multiple views allows you to retrieve winds. And then something which is nice, but also not super FRINGE specific, is that we also plan to fly a thermal infrared payload. And the main purpose is to look at sea surface temperature when there are no clouds, and when there are clouds, we will try to retrieve the cloud top motion. And this will give us a bit data about the wind aloft, which we can combine with surface measurements. Of course, flying in this geometry over land, you're getting your 3D surface deformation motion using the ESA. Flying a formation flying system means that you can reconfigure your assets in space. And we want to do that. So during part of the mission, we will switch from the previous configuration, which is what we call the stereo SAR formation, to what we call a cross-tracking interferometric formation, in which we would move one of the harmonies close to the other one, and forming a single pass interferometer, a bit like TandemX, with of course not the resolution that TandemX can give you by far, but riding on top of the huge imaging capabilities of Sentinel-1. And this opens the door to generating dense temporal time series of surface elevation and surface elevation changes. Now, to give you a bit of an overview of how the mission could look like, so we would, the baseline scenario is to start and end with a cross-tracking interferometric phase of about a year each. And this is in order to retrieve glacier heights at the beginning and at the end, so that you can look at the difference during the duration of the mission. And then in between, we would have maybe 3 years of the stereo formation, which is optimized both for oceans and for the retrieval of 3D motion over solid Earth. Now, let's go a bit into what we want to do with the mission from a science point of view. And I start with a slide showing what you can do already with Sentinel-1. So there's an example of strain rates over Anatolia retrieved using Sentinel-1. And this works very well, and this community knows this works very well. But this works very well because the motion, the information is happening in the right direction. So we are seeing mostly east-west deformation. And you all know that with Sentinel-1, we are very sensitive to vertical deformations and to mostly east-west oriented deformations. It's a bit of a simplified way of saying it, but I think we understand each other. The problem is when the deformation is not happening in the east-west direction, which we can illustrate with an example. So here we're simulating two faults, one like the previous one, oriented east-west in the upper panels, and in the lower panels, you see a north-south oriented fault. And then first we can price ourselves happy by looking at what GNSS would do. So if you only have GNSS and no INSAR, then you don't have the resolution unless you really populate your surface with GNSS sensors. So that's nice for us because we are INSAR people, so we like to add our INSAR data. So what happens when we are Sentinel-1? Now, as expected, we can do a very good job if the fault is west oriented, but we do a very poor job if the fault is perfectly north-south oriented. Add harmony to the mix, and then you see that you get a very good retrieval of your north-south fault. In fact, it looks better than the east-west, but it's maybe an optimistic view by the simulation parameters. Now, what does this bring us? It brings us this. If you put the requirements, which we have set for ourselves, of being able to map, to quantify the stress in all areas with strains larger than 10 nanostrain per year. Then if you rely only on Sentinel-1 or on the current polar orbiting systems, then you can cover about 43% of those areas. Add harmony to the mix, and then by definition of the requirements, we reach 100% because we are designed to reach our requirements. And so it's a very big jump. So this, in practice, it means that you will be much better predict the risk of having earthquakes and the intensity of possible earthquakes in lots of regions where now you cannot do it. To see that we can reach the desired performance, we built, or the colleagues at DLR built a quite complex, quite fully featured end-to-end simulator. We can do it very well because we understand INSAR very well, and we can also benefit from the fact that we have Sentinel-1 data as an input, so we know a lot about the data that we are receiving. We can add simulated deformation. We can add all the errors that we know, so noise, residual synchronization errors, atmospheric, ionosphere, troposphere, and then we can generate time series of interferograms from which you can retrieve the deformation rates in the different line of sights. And then you can combine ascending and descending orbits to get the 3D deformation. And then, of course, because it's a simulation, you can compare the retrieved deformations with what it should be. And here you are seeing the errors for the three components. So east-west, up, down, and north-south. But we are interested in quantifying these errors, and we do this by looking at diagrams. Because we are interested in the deformation and the error in the relative deformation as a function of distance. And we can do it both by looking at these end-to-end simulations or by putting some simplified theoretical models, which for the most part agree with each other. And then what I want to really say about this slide is that we are very close in these simulations to reaching, and we are not really using the full potential of what we have. So I think we will improve. But we're very close to reaching this goal of this would correspond to 1 millimeter per year deformation. This plot shows the relative error as a function of distance between 2 points. And something to highlight is that because of most of the error is coming from atmosphere, the error tends to grow for the up-down and east-west components of the deformation. But for the north-south, because the troposphere is mostly canceling out in the estimation, this error is more or less flat. So we have a north-south performance, which is more or less scale independent, which is very nice and it's very close to our target. So we are quite satisfied with this. And we will also look at a change of topography over volcanoes. I think the salient feature here, so aside that it looks like we can do it, is the fact that we get this dense time series. So if you wanted to compare with TandemX, TandemX would give you better images, but it would not give you the capability of generating this time series images every 12 days or even better. Now I want to switch topics to the cryosphere. And the goal in general, what we can add with Harmony is to look at topography changes, which we can link to mass balances. But we are interested in a range of scales. So on the one hand, we are interested in processes that lead to volume changes in scales of years. So during the duration of the mission, here we are aiming at, you'll see the next slide, so I don't have to repeat it now. We're also interested at looking at fast processes, at things that have an expression in seasonal changes of your ice volumes. And something to highlight here is that the signal that you're measuring in this case, when you look at seasonal processes, is orders of magnitude larger than the long-term trends. So we're talking about variations of height in the order of 50 meters or higher, whereas for long-term trends, we're talking about sub-meter or meter scale variations of the height. And of course, we're also interested in dramatic events to measure the volume before and after the collapse of a glacier, which we can also do. So the first objective would be to provide high resolution and temporally consistent measurements of the ice heights, so volumes, and then later volume changes and mass balance changes over glaciers worldwide. And this is very important because we don't have it right now. So if you look at for how many glaciers in the world we have measurements of the surface height so that we can estimate volume changes, then you see that about half of the glaciers worldwide are not measured at all. So we have a huge gap there. And to make this worse, where we have observations, these are often observations acquired over a decade time with different techniques, which means that when you want to look at what's going on, changes worldwide, you have a very inconsistent view because your data sets are very inconsistent. So with Harmony, we would be able to, in a short time span, acquire the global BM, surface elevation, over glaciers, so we get a consistent view and a consistent estimations of change. So
Paco, there's 2 minutes left.
Yeah, I think I'm more or less on target. Yeah.
Very good.
Okay, so you see our quite ambitious requirements, but it all looks like we will manage. And then the other objective is more process oriented. So we want to look at dynamic processes in glaciers to better understand how it works. When we start losing it, you should realize that a lot of the volume loss is not happening gradually, but it's happening through dramatic events that happen quite fast. So we need to understand these fast processes. And here the uniqueness of Harmony is that we will have the combination of current observations of motion, which we can do using spectral tracking, feature tracking, or your favorite technique, with these very dense measurements of height. And this is a very unique combination, which no other system can provide right now, and it will report an observation gap. And then 2 slides left. This is to tell you where the challenge is when you look at ice volume changes. So measuring the phase center height is relatively easy. We know how to do that. The problem, of course, is where is this phase center height? It's not at the surface, it's somewhere below it. So we have to deal with the penetration in the ice, or with the bias due to the penetration in the ice. Now we have two strategies to deal with it. The first is the easy one. If you're interested in long-term changes, then the trick is to compare apples with apples. So look at the ice at the same time of the year under the same conditions, and then you don't care about the penetration because the penetration is similar, so it cancels out. Of course, you cannot do that when you look at dynamic processes, because you are interested in changes in the volume while the state of the ice is changing. So in those cases, we have to estimate the penetration. And there is a complicated slide, but the summary is that we have evidence that we can estimate the penetration bias with an error of a couple of meters, which compared to the signal levels that we are measuring in this case, in the order of tens of meters, is still quite good. So we can reach our objectives. And this brings me to the last slide before Malcolm kicks me out, which would be a science summary of what we want to do with the mission. Rather than give you an outlook and conclusions, tell you that we are now starting in the phase A and hoping to launch in 2030. I will just leave you looking at an overview of our science objectives, both for the fringe relevant topics and for the non-fringe relevant topics. I'm done, Malcolm.
Thank you very much, Paco, for that excellent overview. Very, very informative, and also remarkably sticking to time, which is much appreciated. I would like to invite my co-chair, Marcus Engdahl, to come up and explain how the question and answer session will work.
Yes, so we are now entering a 50-minute Q&A session. So there are some questions that have been raised on Slido, and we will copy them into this WebEx meeting, and then you can address them one by one. So hopefully it's clear who needs to respond to what.
Okay, then I guess I can start. Just to repeat the questions, one of them is, what is a realistic launch date expectation for OSE-L? And I can, of course, state what the launch date is expected from the contract, and we are currently talking about a launch date for the PFM, so that's the first satellite, in the 2028 timeframe. Now I see I have several questions, which I'll continue then. So the next question I see is also, is it also considered a low baseline for repeat passes in OSE-L like with Sentinel Yes, I mean the ground motion service is one of the major users, or is expected to be one of the major users of OSE-L. Keeping in mind, of course, that baselines scale with frequency, so that the actual baselines flown still need to be optimized, but will be consistent with that objective of measuring surface deformation in the correct way. Let's see. I seem to get most of the questions here for some reason. For OSE-L, how similar will the line of sight be compared to Sentinel-1, and will acquisitions may be in TOPS mode as well? The line of sight is pretty much exactly the same. It's the same orbit, same geometry, so the line of sight would be that of Sentinel-1. And the baseline is not the TOPS mode, but a scan cell mode with a fairly larger bandwidth. Let's see. I have two more, but the next one I'm not sure. It's probably a little bit early. Will the burst IDs be unique among the stacks of acquisitions? That, to be honest,
I guess that's a Sentinel-1 question.
That's more of a Sentinel-1 question.
Yeah, maybe I can jump to answer to this. So yes, this is exactly the ID. So the burst ID will be the same for stacks, and for the same burst on ground, considering the same acquisition modes. So all bursts acquired in IW on the same relative orbit and same location on ground will have the same burst ID, and the same for EW mode.
Very good. Thanks, Guillaume.
If we continue on question on Sentinel-1, there is one related to extended timing annotation. So for this, probably Bethlehem can answer.
Yes, I can take that one, Guillaume. On this one, this new auxiliary file takes in particular in input the PUD precise orbits, and they are available 21 days after sensing. So this will be likely the driver for the availability of these files.
Okay. Does that cover all of the Sentinel-1 questions while we're at it? Seems so. Let me see. So that was the burst ID. I have one more on Sentinel-1 NG, and then I would like to hand over to Paco for the harmony-related questions. The question is, for Sentinel-1 NG, will the TOPS IW mode stay as the backbone SAR mode over land, or are there new different SAR modes in consideration? Well, I can certainly point out we're at phase A right now. So new and different SAR modes are definitely being considered, but with the objective of having the maximum continuity with Sentinel-1 and the Sentinel-1 applications. But at this point in time, no baseline choice of mode has been made. The trade-offs will be studied, and they will be evaluated not in a closed room, but together with representatives of the different applications, and then we see later on this year, beginning next year. Okay, Paco, would you like to take the harmony one?
I can do that. I see two questions.
Yes.
The first one was on the tier. Now this is on oceans, and the tier is going to give you. So primarily, when we put it in was to look at SST. Now we also look at clouds with it. If you consider SST, you have to imagine that basically we're trying to get the full picture. So if we could, we also fly together a little SMOS with high resolution to also get salinity. Yeah? But you want to get as complete a picture as possible. So if you look, for example, at surface currents, then they are often related to density gradients, which are related to temperature changes. So the SST can be the cause or that causes the currents, but not always. So having the SST allows you to better understand the processes that you're looking at. SST changes also affect the marine boundary layer, and we are interested in looking at the marine boundary layer, so we want to see the relation between SST gradients and how turbulence above the surface changes, for example. Now, there's another question, which is the question. I think that the summary is why do we need GPS if we have harmony? So it seems that harmony could obtain good TV information, but there's an advantage of GPS networks. I think in general, when you work with SAR, you have very good relative measurements, so you're very good point to point, but you often need to anchor it to something. And we also have phase tapping issues and things like this. But basically, for me, you want an anchor. So you need to have some reference measurements to which you can anchor where you can tie your very high resolution and dense data produced with your INSAR. So I think that's the answer.
All right, thank you, Paco. Marcus, you can help me too. Let's see, the harmony, the latency, the timing. There's one to Pierre here. Is it possible to request to process old SLCs with new IPF corrections? Sounds like a question for the mission manager.
Yes, unless Bethlehem want to help me on that one with the new configuration.
I can comment on that one on the operation. So there is no mechanism today to request the processing of previous SLCs with a more recent IPF version. There is no mechanism today made available to the users and no interface that is allowing this. We are foreseeing two things for the future. One is that we are foreseeing the possibility to have a non-request capability, so that in terms of data access, it will be possible not only to retrieve a previous SLC, but also to make an on-demand production using a more recent IPF version. And this is planned for, I would say, realistically, mid-2022. With, I would say, maybe something to mention as well is that this capability will come with, of course, a predefined capacity embedded with it. So that will not be an unlimited capacity of requesting reprocessing of previous SLCs. And the other thing that we are considering as well is the possibility of complete reprocessing. We know that there have been some changes on the IPF at certain points in time that have interrupted the time series or created a change in the time series for the SLCs. And for this, we are considering the possibility in the future to do a full reprocessing campaign, a little bit like in the mode that this is done for optical missions. So this is at the moment one possibility. We are making this possible from a technical point of view. We need to see if this will be feasible also from budget perspective. And in that respect, if there are specific requirements or specific needs coming, say in particular from this community, I think this will be the right forum to take note of this and to take the recommendation with us.
Okay. Thanks, Bethlehem and Pierre. So just following up, keep in mind the idea of, as this workshop progresses, of perhaps ensuring that there's a recommendation that the community can stand behind in that sense. As far as I can make out, Marcus, we've addressed most, if not all, the questions. There is one question at the very beginning, which is, will the recording of the presentations be available for later viewing? And maybe you can answer that one.
Yes, so they will be.
They will be, okay. And then
while we wait for the possible last question, I would like to make an announcement. So the ESA Living Planet Symposium 2022 will take place in Bonn from the 23rd to 27th of May 22. And there are some deadlines approaching. So if you go to the Living Planet 22 website, which is live, you will see that session proposals, they have a deadline of September 2021. So if you want to propose sessions for this big ESA organized EO event, please do that by September. Thank you.
Right. Thanks. We have one more question, and then I think we can close the session. I'll just read it out. It would be useful to reprocess with the new tools Sentinel areas impacted by RFI as a priority. Is this being considered? I think this ties into something that we discussed previously. Could you try and answer the question?
I think it's more a recommendation, and which is taken on board, and it's related, I understand, to the reply made by Bethlehem on the fact to reprocess based on some particular versions of the processor.
Yeah.
Maybe we could. I would like to perhaps to, I want to say, to challenge this kind of recommendation, but maybe to put a caveat in that, in the sense that at the end, the areas impacted by RFI are relatively few. We are estimating the amount of data that is affected by RFI by less than 1% of the acquired data. So I would have expected, but again, this is really an open question, and I would say really open for during the meeting before the recommendations are made, that such kind of recommendations for priority would be targeting perhaps time periods where data had been processed with different IPF versions that are not consistent with the current one. So perhaps one way of looking at the recommendations will be by time periods or data processed with a specific IPF version for which this continuation is not ensured today.
Right. Okay. So also a general recommendation, at least for us, you want to propose things. Be sure to document the context and the scale and the justification for why you think it should be a priority, and take into account what's available. Okay, with that, Marcus, it's 1 minute before 12:30. Any last comments on the session and before we close?
Well, thanks to all the presenters, and I think that we are on schedule, and we can break for lunch. And after lunch, we are starting at 1:30 with Advances in INSAR Theory and Methodological Innovations, session 1.
So please join up again at that point in time. Yes. Thanks to all the presenters. Thanks to my co-chair, Marcus, thank
you, Malcolm.
Look forward to the rest of the presentations and discussions in the coming week.